I'm hoping to share the sacred burrito delicioso with your friend, you. Remember, you in our previous examples were this person over here. X, we call that position. So your position right now is -4. You are positioned at 4 meters behind or to the left of. That's what we use to denote the negative sign. It means direction. So you're to the left of, or we could say to the west of, blah, 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 blah. The origin of all things, the origin of the universe, the origin of the order of all cosmos, the origin, the beginning, the end, the burrito delicioso. So you travel to the origin where you grab the burrito, and then you can continue traveling forward until you reach your friend. The entire journey took 14 seconds. So last time we were kind of discussing different ways of answering the question, how far does an object travel in its motion? And we saw that there are different ways of doing that, distance and displacement. We got into talking about scalars and vectors. Well, I want you to think about it. If there are two different ways of answering the question, how far, and those two ways are distance and displacement, or delta x, then there must also be two ways of talking about how fast an object goes. How fast is it traveling? What is its rate of motion? What if we use the distance? So what distance did you travel? Well, you went forward 4, grabbed the burrito, then you went forward 3, 7 meters. And then how long did that take you? What was the time? 14 seconds. So now we have a way of talking about how fast using distance. 0.5 meters per second. 0.5 meters per second. That's how fast you went. You were going half a meter per second. Now, it's really important to me that you guys understand what this unit over here means. This is called a combined unit, where we have two different measurements stuck together, meter per second. This means that if we were measuring the motion for every 1 second, per 1 second, there's an invisible 1 down here. For every 1 second, you would have traveled half a meter, 0.5 meters. Another way of saying is that every 0.5 meters that you travel, 1 second of time elapses. That's how a combined unit works. So that's the distance. What about displacement, delta x? Well, I think you're already going to see that's going to end up being the same. Final position minus initial position, 7 meters. It still took you 14 seconds. So once again, we get 0.5 meters per second. But I want you to think about this. Are these two really the same? Numerically, they are. This one was using the idea of distance over time. This one used the idea of displacement, delta x over time. Distance, remember, never, ever has a direction to it. It's always going to be a positive number. So you're always going to get a positive value over here. Displacement, though, can be positive or negative, and it matters. The fact that the displacement was a positive 7 means that you went to the right, to the east, forward 7 meters in 14 seconds. So maybe we should emphasize that there is a positive here, and this tells us something important. It tells us that you traveled to the right. With distance, there's no actual way for us of getting that information. So we have two different ways of talking about how fast something is going. We call those ways, the two different ways of discussing how fast an object is going, speed and velocity. Speed is a scalar quantity. It will never have direction because it uses the perspective of distance over time. Velocity, this is the big daddy of this unit. It is a method of discussing how fast an object is moving. This whole unit is about motion. Things that are in motion have a fastness, they have a velocity. But this time we're using the perspective of displacement over time. So this is very important. We have another equation. Velocity is equal to delta x over t, the displacement over time. And the units are meters per second. Remember what a vector quantity is? This is a vector quantity. Vectors always have directions associated with them. Well, how do we talk about direction? Remember, that means that we're going to have a positive or a negative. Speed is scalar. It's always just going to be a number, a size, a magnitude. It's always just going to be a positive number, and that positive number does not actually mean anything, okay? And still even more, there are two different types of velocity that we can talk about. We can talk about the velocity for the overall entire trip, and that is going to be known as the average velocity. Or we can talk about the velocity at one instant in time, which may change during the course of the trip, and that's known as instantaneous velocity. We'll talk about that a little bit later on. Let's look at this example. What is the average speed, average velocity, instantaneous velocity, instantaneous velocity? So let's take this question first, the average speed. Remember, speed is distance traveled divided by time. So what's the total distance traveled? 1, 2, 3, 4, 5, 6, 7 is the distance. Are we worried that the friend went backwards? No, because it's distance. Distance never has a direction to it. It's scalar, and so speed will be scalar. How long did that take? Our overall time is going to be 12 seconds. In this class, please never, ever, ever, ever use fractions. We will always use decimals. So 7 divided by 12, 0.583 meters. That was our distance unit. Divided by 12 seconds, meters per second, 0.583 meters per second. What is the average velocity? This time I think we're going to see that it's going to be different. Remember, velocity is equal to delta x, displacement over time, -4, that's the final position, -4, minus, the initial position is 3, divided by 12 seconds, -7 meters, over 12 seconds, -0.583 meters per second. Velocity tells us that this person went backwards. Velocity has a direction. It is a vector measurement. The negative sign here tells us what? It tells us that our dear friend traveled overall to the left, backwards. Notice also what we found was the average velocity, because it was the velocity for the entire trip. We looked at the entire displacement, the entire time. That was the average velocity. Let's now go, though, and try to figure out what the instantaneous velocity is going to be. Notice I ask you in this way. What's the instantaneous velocity when this person is at x equals 2? Remember, x is position. So I'm asking you, when the person gets to this point right here, how fast are they going at that instant in time? Well, I think you'll notice that this person is actually traveling at different speeds throughout the trip. Remember, the journey has 2 phases. This part of the journey takes 4 seconds. The next part of the journey takes how long? 8 seconds. We found the average velocity by looking at the overall trip, but now I'm interested in this part of the journey, at this instance, when this person is right here at that moment in time. What is their velocity? We're going to look just at this portion of the trip. If we can find the velocity there, I think we can say that we found the velocity at that instant in time. So instantaneous velocity is just the velocity that we're going to calculate the exact same way, but it's just kind of zoomed in for this part of the journey. So delta x over t, zoomed in, focusing on this part of the journey, they end up at 0. They started at 3, and that whole thing took 4 seconds. That is their velocity for this part of the journey. That's their instantaneous velocity when they are right here. And once again, what does the negative mean? Does negative mean they're going really slow? No, not at all. That negative means direction. They went to the left. Ooh, spoopy. All right, let's find the next instantaneous velocity at x equals -2. So now I'm worried about this part. -4. Where did he begin? Remember, we're just looking at this leg of the journey. So for our purposes, that's beginning at point 0, the origin. And how long did that take? Once again, just this leg of the journey, 8 seconds. -0.5 meters per second. That's the instantaneous velocity for this next leg of the trip. So we have discovered some actually helpful, useful information. We know that this person was going faster during which part of the trip? During this first part of the trip, because their velocity is larger. Remember, that negative doesn't have anything to do with largeness or magnitude or size, just the direction. So comparing 0.75 to 0.5, 0.75 is bigger, so they're going faster there. What do the negative signs mean? Once again, they mean direction. Okay, here's a link in the PowerPoint that gives you a pretty good idea of this talk about instantaneous versus average. So you can see that the speed at every instant in time is constantly changing. And we can also take the average speed. I think you can see the average is going to be pretty easy to find. They go a total of 5 miles in 0.2 hours. Distance over time, 25 miles per hour was their average speed. Another little example for us. Very excitedly travel to the origin to obtain the sacred burrito and carry it to your friend. And as you're going, you take some data. Let's look at the data. It looks like this time, every single second, you are noting your position in meters. So if I wanted the average velocity, so your velocity for the entire trip is 3.5 minus -4, 7.5 divided by 5. 1.5 meters per second was your average velocity. Notice this is a velocity because it's positive. This is telling us you went to the right. But notice that from this data, we could actually calculate some instantaneous velocities, the velocity as you go. And your velocity at time 0 is going to be 0 because you're just standing still, you haven't moved yet. But let's find the velocity for the first second of travel. You change your position. Here's your final, here's your initial, and it took you 1 second. Positive 0.5 meters per second. All I'm doing for each of these is delta x over t. This time my delta x, you end up at -2.5. You started at -3.5. That's a change of 1. And that took you 1 second. So this time your velocity is +1. Oh, look at that. You are speeding up. You must be excited. Positive 1.5. Oh my, you've sped up again. From -1 to 1, that's a delta x of 2. That took you 1 second, so that's going to be +2 for the velocity. And then it looks like you go from 1 to 3.5, and that takes you 1 second. That's going to be +2.5. Oh my, look at that. You have been speeding up the entire time. You did not travel 1.5 meters per second the whole way. That's just your average overall, going from your initial to your final position and the overall time. But you had different instantaneous velocities the whole way. Now that's very curious. And if we look at this data, you'll see that it looks like you were very steadily getting faster and faster. We did not even have to look at the velocity data to know that you were speeding up. We could have just glanced over here and saw that every second that elapsed, you're traveling a farther distance. Your instantaneous velocity is getting faster and faster. What the heck does that mean? Well, my friends, that is known as acceleration.